All right, so today is still on probability, but we're going to shift gears into more of traditional probability problems that we covered in chapter 5. These are ones that have some formulas involved, so you're going to want to write these on your formula sheet that hopefully you've been starting. I mean, you have access to the formula sheet that we've been using all year long, and the one on the back of the z-score chart, but I would suggest maybe making your own formula sheet that's a little bit more understandable and a little bit more organized. So anyway, here's our first set of formulas that you're going to want to write down. These were not these were not on the formula sheet that AP would have let you use. So now that you are allowed to use your notes, definitely write them down. These are when two events are independent. Now, you might have problems where they ask if two things are independent, and if so, you would have information about probability of A, you would have information about probability of B, and you would have information about the probability of A and B. And what you would do is see if this equation holds, if when you multiply these together, you really do get this probability. If that's true, then you know they're independent. You can also use your conditional probability formula, and if the probability of A given B really equals just the probability of A, then you can say that the two events are independent. This also works the other way around. If you are told that two events are independent, then it's like you can unlock these formulas. So we're going to do an example in a little bit that involves these. We'll come back to them. If you have, now go back, sorry. This is and, remember? So if two things are occurring at the same time, then it would be an and. Or the problem might actually use the word and. Here's your formulas that you're going to want to write down if the problem is an or problem. So the probability of A or B is when you just add the two probabilities together. Now that is if they are mutually exclusive, meaning there's no overlap whatsoever. Then you just straight up add the two probabilities. But if there is an overlap, you have to subtract it. You still add the probability of A and the probability of B, but you subtract that overlap. Now, I don't really think there's going to be Venn diagram problems involved, but what I want you to remember is that if you were going to shade in the probability of A or B, it is everything in the circles. Okay, everything in A, everything in B, everything that they have in common would get shaded. So you are counting the probability of A and B, this middle region here. You are counting it, but you're only counting it once. So when I first taught you this, I showed you that, okay, here's the probability of A, everything in this teal bubble, which includes A and B. And then here's the probability of B, everything in the yellow bubble, which includes A and B again. So we already counted it. We counted it once in the yellow bubble. We counted it once in the teal bubble. So we counted it twice total. That's over counting it, so that's why we're subtracting off one of them. We want it, we just only want it once. So I personally would write this formula down on your formula sheet. Okay, anytime you have a problem that involves or, I would break out this formula. And just know that if there's no and, so if they are mutually exclusive, there's no overlap, there's no and, then you would just be subtracting nothing. You would have probability of A plus probability of B, and you would be subtracting nothing, and that doesn't hurt anything at all, and that transforms it into this formula up here. So I would just go with the one in the box. This is your formula for conditional probability. This is the probability of A given B. So if you have the sense that B has already occurred, then you would use this formula. So this symbol right here means and. So we would do the probability of A and B on the top, and then whatever you're given, that is the probability that goes on the bottom. So we have a couple examples coming up that are going to use this formula as well. All right, so oftentimes mutually exclusive and independence are what kind of give people trouble. So let's kind of go through this example to distinguish the two. So let's say we are selecting one card, just one card from a standard deck of cards. And event A is the probability that the card is red, and event B is that the card is a 7. So the first question is asking, are these mutually exclusive? So ask yourself, is there any overlap? So can one card be both red and a 7? And the answer is yes. A single card can be both red and a 7. We've got the 7 of hearts and we've got the 7 of diamonds. So these are not mutually exclusive because there is an overlap. Okay, now are they independent? Well, that is a little harder to just reason through. So that's why we have these formulas from the beginning here. So if I can use these formulas and prove that the left really does equal the right, then I know for sure that they are independent. So let's try those. Let's try this one. And we're going to see if they really do equal the probability of A and B. All right, so the probability of A is that the card is red. So what is the probability of having a red card? Well, half the deck is red, right? So the probability of the card being red is 1/2. The probability of B, the card being a 7. Well, there are 4 7s in a deck out of 52 cards. Probability of A and B being both red and a 7, that happens twice. 7 of hearts, 7 of diamonds, that's 2 out of the 52 cards. So do these two statements really equal each other? Well, if you multiply 1/2 times 4 over 52, you are going to get, oops, I got to erase that. When you multiply them, you will get 1 over 26. And that is the same thing as 2 over 52 when you reduce it. So yes, they are independent. Now, if this was on the AP test, write a sentence. Oftentimes, you need to back it up with some sort of formula like this. So like refer to the fact that you tried this formula, show your work, write a sentence about the fact that you know that they are independent. Okay? All right, so let's do an actual problem here. All right, the table below has information about a survey about whether a person wears contacts, glasses, neither or both, and then it's also showing gender. Now, these decimals, these are all probabilities, and I can tell that because look at your total is 1. So keep in mind that these are already probabilities. So A is asking, it's saying one person from those surveyed will be selected at random. What's the probability that the person selected would be someone who wears contacts and who is a man? Okay, now, I don't need a formula for this. First of all, I'm not told if they are independent or not. Okay, so I'm not going to use a formula. I am given a chart. I can see it in the chart. Someone who wears contacts and is a man is right here. Okay, so no formula necessary. I can see it in the chart, 0.02. Okay, now part 2. What is the probability that the person selected will be someone who wears contacts or who is a man? Now, this is definitely one I'm going to use a formula for. The probability of or is back here, right here. So we're going to do each individual one added up, and we're going to subtract the and. So in the context of this problem, it would be the probability of wearing contacts plus the probability of being a man minus the probability of wearing contacts and being a man. All right, so the probability of wearing contacts, that total probability is right here, 0.0790 plus the probability of being a man. So the total probability of being a man is right here, 0.4802 minus the probability of wearing contacts and being a man. That's what we figured out in part 1. AP likes to do that. They like to do problems where you find something and then you use it in the next part. Now, that's not always the case, but they do like that. So when you calculate that, you're going to get 0.5392. Okay, part 3. What is the probability that the person selected will be someone who wears contacts given that the person is a man? So I'm going to write that out in symbols. Probability that the person wears contacts given that they are a man. We have a formula for conditional probability back here. So I'm going to do the probability of and on the top, and then whatever I'm given is what goes on the bottom. So going back here, the top is going to be the probability of contacts and man. And then on the bottom is going to be whatever I was given, which is the probability of being a man. Okay, contacts and man. Again, that's what we found up in the first part of the problem. The probability of being a man is 0.4802. And when I divide those, I'm going to get 0.0416. Okay, so these are nice probability questions because we have formulas we can follow. So I really want to make sure that you are writing these formulas down. All right, here's the same scenario, but now this is part B of the question. So this is a true AP format where part A might even have 3 parts to it. So here's part B. For the people surveyed, are the events of being a person who wears contacts and being a man independent? So we have to justify if they are independent or not. So the way we can do that, go back here, we can use any of these formulas to try to verify that. So let's try, is the probability of wearing contacts times the probability of being a man, is that really equal to the probability of wearing contacts and being a man? All right, so the probability of wearing contacts, the total is 0.0790 times the probability of being a man is 0.4802. Is that equal to the probability of wearing contacts and being a man? Again, contacts and being a man is 0.02. So let's test it out, see if that actually works. When you multiply these two together, you're going to get 0.037936. And that does not equal 0.02. So these are not independent. Another way that we could try to show this is by using our conditional probability formula, which says that the probability of A given B should just equal the probability of A if they really are independent. So we did that back here where we did the probability of wearing contacts given being a man. So let me go down here again. Probability of wearing contacts given being a man should, if they're independent, equal just the probability of wearing contacts. And we found in the last problem that this probability of wearing contacts given being a man, we found on the last page that that was 0.0416. And does that equal the probability of wearing contacts? I've got to scroll up for that now. So, having trouble scrolling. The probability of wearing contacts, that total is right here, 0.0790. So it did not equal that. Oops. Technical difficulties. What was it again? I think 0.0790, I want to say it was. In any case, they do not equal, they're not independent. So you can show it a couple different ways, is the bottom line. Okay, this is a different question here. So approximately 24% of students at a particular high school have a paying job. Of the students who have a job, 36% are also involved in school activities. Of the students who don't have a paying job, 58% are involved in school activities. What's the probability that a randomly selected student from this high school is involved in activities? Okay, now I know that a lot of times when students read these kinds of problems, they're just instantly overwhelmed because of all of the information that was being given. When you get that sense, I want your instinct to be, let's make a tree diagram. You do not have to in order to solve this problem. It's just one method. And so it might just be the thing that helps you through a problem like this, especially if you get the sense that you have two paths, either this or that. So in this problem, it looks like you have a job, but you might not have a job. And then you might be involved in school activities, or you might not be involved in school activities. So let's kind of start with the given information. So it said approximately 24% of students at a particular high school have a paying job. So I might have a job. And that was 24%, so 0.24. But I might not have a job. Well, if 24% have a job, then 76% would not have a job. Just do 1 minus 0.24, you'll get 0.76. Of the students who have a job, so of these students right here, 36% are also involved in school activities. So 0.36 of these people that have jobs are in school activities. Okay, now you might have a job and not be involved in school activities. So if 36% of these people are in school activities, then do 1 minus 0.36 and you get 0.64 who are not in school activities. Of the students who don't have a paying job, so of these students here, 58% are involved in school activities. So 0.58 are in school activities. But you might not have a job and you might not be in a school activity. So 1 minus 0.58 is going to get you 0.42. All right, now whenever I make a tree diagram, I figure out the final probabilities for each branch. And those would be the and probabilities. So along this branch right here, these are people who have a job and are involved in school activities. So I'm going to do 0.24 times 0.36, and I'm going to get 0.15. Oops, sorry, I did that wrong. Okay, I will get, when I multiply those two together, I will get 0.0864. Okay, now I could find the probability of having a job and not having a school activity. That would be 0.24 times 0.64, and that's going to give me 0.1536. I could find the probability of not having a job and being in school activities. That would be 0.76 times 0.58. And that will give me 0.4408. And then the last one is not having a job and not being in school activities. That would be 0.76 times 0.42. And we will get 0.3192. I always find those just in case. I'm going to need them because I probably will. So I haven't even really read the question yet. It says, what's the probability that a randomly selected student from this high school is involved in activities? Well, look, I can be involved in activities this way, having a job and being in activities, or I can not have a job and still be in activities. So I can be involved in activities this way, and I can be involved in activities this way. So I'm going to add those two up because it's one or the other. So I can have a job and be in activities, or I cannot have a job and be in activities. So I add those two things up, and my final answer is going to be 0.5272. So that answers part A. Part B, what's the probability that a randomly selected student from this high school has a paying job given that they are involved in school activities? That's a conditional probability. So I'm going to write it out. Has a job given they are involved in school activities. All right, so our formula for conditional probability, if we go back to here, we do the and probability on the top, and then whatever we're given goes on the bottom. So I will have the probability of having a job and being in school activities on the top. And then on the bottom will just be the probability of being in school activities. All right, well, the and probabilities were what we calculated here in red. So having a job and being in school activities, having a job and being in school activities is this top one right here, 0.0864. And the probability of being in a school activity, that is what we found in part A. What's the probability of being involved in activities? So we already found that in part A. That was our answer to part A, 0.0, oops, not 0.0. Fix that, 0.5272. And when you divide those two things, you're going to get 0.1639. Again, they like to use problems where you take what you got in part A and use it in part B. Just know, though, on the AP test, if you get part A wrong, but then you use it correctly here in part B, you're still going to get some credit. Okay, and then this is our last example here. So, actually, I think I'll make a separate video for this one. I'll stop this video and I'll make a separate video.